Experiment 167, the Daniell cell. In this experiment we explain the Daniell cell and we show how to make one. The Daniell cell is the ancestor of the battery, without which modern life is hardly imaginable. To start with, we show you what happens when a zinc plate is placed in water and the voltmeter is connected to both the zinc plate and the water. We notice a potential difference between the zinc and the water, the zinc plate being negative and the water being positive. The explanation for this phenomenon is that zinc prefers to ionize rather than to remain metallic. The ions migrate into the solution, leaving the electrons behind in the plate. An equilibrium state is reached when the chemical tendency to ionize counteracts the electrostatic force to drive the positively charged ions back to the negatively charged metal. We then repeat this procedure with a copper plate. We barely see any potential difference. It is not very surprising because we know copper to be more noble than zinc. Could copper prefer to be metallic rather than being dissolved? In order to answer this question, we have to compare metallic zinc in a zinc solution with metallic copper in a copper 2 solution. We take two beakers, one filled with a 1.0 molar zinc nitrate solution and the other with a 1.0 molar copper 2 nitrate solution. As in the first set of experiments, we place a zinc plate in the zinc solution and the copper plate in the copper 2 solution. We measure the potential differences between each plate and its solution. Here again, the zinc plate appears to be negative, confirming our explanation that zinc prefers the ionic state. The copper plate, however, turns out to be positively charged. Apparently, copper prefers the metallic state. Therefore, copper 2 ions precipitate on the copper surface. When we connect the two plates with a wire, we allow the abandoned electrons in the zinc plate to migrate to the precipitated copper 2 ions in the copper plate. Again, an equilibrium state between the chemical drive to migrate from zinc to copper and the electrostatic force resulting from the potential difference between the solutions will be reached immediately. So far, we have shown that electrochemical reactions are capable of separating charges and hence of the transportation of energy stored in the electrons, however, for a short time only. To use the system as a power source, the electrical circuit has to be closed, so that the counteracting electrostatic force does not play a role any longer. In order to do so, we connect the solutions with a salt bridge, a glass tube filled with jelly and sodium nitrate. Now, the surplus of negative charge in the copper 2 solution is immediately compensated by the migration of sodium ions in the copper 2 solution. The surplus of the positive charge in the zinc solution is cancelled out by the nitrate ions. The electrical current can now flow until one of the reactants is exhausted.